Almost 8 years ago, when this channel was fresh and before I had gray hairs in my beard, in fact, before I had a beard, I made a video showing that if you take a grape and cut it almost completely in half and put it in the microwave, you can make some plasma.
Oh, go the laws of physics.
Yeah!
Oh, yeah! It's still going!
But the explanation we had in that video was lacking. This was me and my friend Dr. Stephen Bosey, a fellow physicist. So you should look forward to that on another episode of Veritasium. To be honest, nobody really knew how this effect worked. That is, until now. As of the publication of this video, 3 scientists have published an explanation in the Proceedings of the National Academy of Sciences. They studied this effect with high-speed cameras, thermal cameras, electromagnetic modeling, and they came up with an explanation that I think is pretty satisfying, and it extends way beyond just microwave grape plasma. So naturally, I called up these scientists.
Yeah, I actually saw your video before, like your videos before joining the Grape project.
Oh, really?
Yeah, so I was like already kind of like interested before joining the project.
The scientists showed you don't even need to use a grape. You can get the same effect with hydrogel water beads. These are those tiny polymer beads which, when you soak in water, they increase in volume like 100 times. To understand how microwaving a grape gives you plasma, we first need to know a few things. Like, a typical household microwave uses a frequency of electromagnetic radiation at about 2.45 gigahertz. That means that the wavelength of microwaves inside the oven is about 12 centimeters long. Now, if you've ever studied electromagnetic radiation, you might have the intuition that interesting things start to happen when the object or obstacle is around the same size as the wavelength, which a grape certainly is not. It's not 12 centimeters. But the important quantity is how big is the wavelength inside the object, inside the grape. 12 centimeters in air, but the index of refraction of grape material must be close to like 1.33 or something, right?
Yeah. So at visible wavelengths it is a lot lower, but in the microwave regime the index of refraction is like almost 10. So you have a much higher index of refraction.
So microwaves are traveling, like 10 times slower through the grape than they are through air.
Yes.
And that means that the wavelength is 1/10 its size through air. So instead of 12 centimeters, it's about 1.2 centimeters. Right about the size of a grape. Now, if you take a single grape and place it inside the microwave, don't cut it in half, what you find is that the microwaves actually become trapped inside the grape. And that's because of its high refractive index and its size.
Because it turns out that when you have like a ball where approximately the diameter is roughly the same wavelength of the microwave in the material, actually turns out that it can be trapped in there. So it interacts, it bounces at the borders of the ball, and it can't get out.
Is it like total internal reflection?
Yes, pretty much.
Wow, that's interesting. I hadn't thought of it that way. So the microwaves become trapped inside the grape, and they actually form these resonant modes. You can think of them as standing waves, just ways in which the electromagnetic fields like to oscillate inside a grape, such that the maximum electromagnetic field is actually in the center of the grape.
When you put it in the microwave, you see that it heats up not from the outside in, as you would expect, as if it were just absorbing the microwaves, but rather from the inside out.
If you add a second grape to the microwave, you see that the same thing happens. The microwaves get trapped in the second grape too, and the amplitude is highest in the very center of the grape, and so the heating occurs most of all there. But if you move these 2 grapes close together, so they're closer than, say, a wavelength, well, then you can start to get interactions between the electromagnetic fields in the one grape and in the other. And in fact, if you get the grapes touching, then the greatest electromagnetic field actually occurs at that contact point between the 2 grapes. And so that is where you're going to get the greatest oscillating electromagnetic fields, and that is where those grapes are going to get hottest. It's also interesting that you don't need to cut the grapes in half. 2 grapes placed side by side will make this effect work, as long as they stay in contact.
So that's why in a lot of the videos you see there's a watch glass. So the reason the watch glass is there is to keep the grapes together.
Now, with the very strong electromagnetic fields at the intersection of the two grapes, what you can get is some sparks, some breakdown of air. That is, the electric fields are strong enough that they ionize the air, creating those sparks, and that is what leads to the plasma. It creates these ions, which can then receive more energy from the microwaves. You can see it here pulsing at 120 hertz. That's twice the 60 hertz frequency of mains power, which reflects the fact that the amplitude of the microwaves is pulsing twice every cycle. And what is that plasma made of? Well, the scientists looked at the spectrum of the plasma from a grape, and they found that there's a strong potassium emission line and also a sodium emission line. So it seems like those ions must be pretty common in the grape, and when the plasma gets formed, is those ions which are sprayed up into the air, and that is what we're seeing.
Whoa! Who needs drugs?
Now, the size of the grapes is important, which is something I, of course, suspected because you don't see this happening with too many other squishy fruits. But you don't have to get them the exact right size. And this is because water absorbs microwaves. So the scientists did some modeling of this, and if you had a material inside the grape that did not absorb microwaves, then what you would see is at certain particular sizes you get extreme amplification of the electromagnetic fields. It's basically one size that you'd have to hit to get the amplification. But made of an absorbent material like water, this broadens out the peaks, so you get less amplification of the field, but over a broader range of sizes. This is why a lot of grapes will work, even if the sizes vary. So, in terms of like applications of this research, what do you think? I mean, obviously, people like me are excited because this is a fun trick. But beyond that, what do you think in terms of like applications of this?
The main limit in fabricating microchips right now and going smaller and smaller is the lithography. So, how to make these very small features.
This phenomenon shows that two spheres of the right size and refractive index can focus electromagnetic energy down to a tiny spot in between them. In this case, down to around a millimeter from radiation with a 12 centimeter wavelength. If similar focusing could be achieved with light, it would provide a significant improvement over current lithography techniques.
So if we could somehow harness this to do this lithography, to be able to maybe write things very small, you could actually use light to make really small features. You could do like every 2 nanometers mark spot with about 2 nanometers resolution.
It would help continue this like Moore's law.
Mm-hmm. Yes, it would help continue Moore's law, like putting small things in a single chip.
So I'm glad I was finally able to explain how this effect works. Did you enjoy it? Do you feel like you get it? Any questions? Put them in the comments below. Also, I really like this video that I made. This is my previous video, and so if you haven't seen it, go check it out. I'll also put a link to the original grape video, which is maybe not that good because it was 8 years ago. But anyway, thanks for watching.